In this video, we're going to talk about the essential solid geometry concepts that you would need when you're going to take calculus. Now, for one thing, we are now going to go out of analytic geometry, which is the combination of algebra and geometry, and we're now going to solid geometry. For one thing, one difference is that we do not need algebraic expressions anymore to represent our figures, although algebra will still be vital in solving problems regarding solid geometry. Further, we're going out of the plane, we're going to extend from the plane to solids. That's why we're going to go solid geometry. Now, solid geometry deals with the mensuration or the measurement of three-dimensional figures called solids, and the solid geometry treats primarily figures of all of whose elements do not lie in the same plane. So for us to be able to grasp that concept, we have first to go back to the plane. So the plane is one of the three undefined terms in Euclidean geometry, the other two being the point and the line. So a point, we recall, is described, it's not defined, because the point, the line, and the plane are undefined terms. So we simply describe a point as a location in space. But that's it. We don't know how big it is. A point can be as big as the moon or as small as the tip of your ball pen. So a point is a location in space. And a set of points that extends indefinitely in both directions is a line. So that's how we describe a point and a line. Although technically we don't know what they are, because we cannot define them. So another undefined term is the plane, which we describe as a surface such that a straight line, that should be a straight line joining any 2 points in it lies full in the surface. And it's understood to be indefinite. And although usually we represent it as a quadrilateral like this, it doesn't actually have a shape. One reason why we represent it by a quadrilateral or a four-shaped polygon is because it shows that it has two dimensions, length and width. So you have your length and width. And the plane is usually determined by either three non-collinear points, two intersecting lines, or two parallel lines. Now, when we say collinear points, these are three or more points that lie on the same straight line. Hence, if we're going to have 3 points that are non-collinear, meaning those three do not lie on the same line, then we can determine a plane. But these points should be coplanar. These are points that lie on the same plane. And we also have coplanar lines that lie on the same plane. So now that arises the question, does that mean we have non-coplanar points and non-coplanar lines? Yes. Take a look at this figure here. We can say that points A, B, and C are coplanar points. A, B, C are coplanar because they lie on plane M. However, we say that A, D, and E are non-coplanar because although D and E lie on plane N, A does not. So this makes A, D, and E non-coplanar points. Similarly, since we know from plane geometry that 2 points determine a line, if I create a line from point B to point C as such, let's realign that here. Oops. Better there. Just extend that. Okay, there you go. So, I have this line here, BC, and then the line that contains F, D, and E. They look like they're in the exact same direction, but they're on different planes. This is on plane M, this is on plane N. Hence, they are non-coplanar lines. However, these lines HG and FT, they are on the same line, and hence they are coplanar lines. And since we're in solid geometry, we're going to talk more about these. We have two different planes, rather, and those elements that are within these respective planes. Now, since we are talking about planes in general, if we have two planes that intersect, or two planes that intersect, then we can form what we call a dihedral angle. Take a look at this figure. Say, for example, this plane here, this plane and this plane are intersecting, all three of them. Now, of course, we describe rather a plane as indefinite. Hence, these planes are continuing in all directions. It's just that they intersect specifically here. So this is how we represent the intersection. So now the angle formed by two half planes or the planes intersecting is what we call a dihedral angle. In this specific case, we have a dihedral angle here. Let's mark that in blue. This is one dihedral angle. Another dihedral angle because it's two planes. And technically, this one in red, from this angle from plane B to here, that's also a dihedral angle. So the angle does not just it's not just here, but it's this entire opening as long as where the planes would intersect. So the line common to the half planes, this one is what we call the edge. This one, this line here, this line here is what we call the edge. And then two dihedral angle, that's what we call the edge of the dihedral angle, and the two half planes are what we call the faces. So these two are the faces of the blue marked angle, these are the faces of the green marked angle, and these are the faces of the red marked angle. So, if two half lines, one on each side of the half plane, like this, are drawn perpendicular to the edge of the dihedral angle, that's why you have 90 degrees marked here, of the dihedral angle at a common point here, then these lines are called half lines. These are called half lines. And the angles in between them, the ones that we actually mark, is what we call the plane angle of the dihedral angle. Because this and the entire opening from the in between the two planes is the entire dihedral angle. But the ones that we mark here, here, and here are what we call the plane angles. It's just that we don't have a plane angle marked in red because we don't have line segments that would cover here. Why did we mention the plane angle? Because the measure of the plane angle is the one that defines the measure of the entire dihedral angle. So if we want to measure the dihedral angle, we just need to measure one plane angle within the dihedral angle. If the dihedral angle is just from the intersection of two half planes, then the polyhedral angle is the angle formed by three or more planes which meet at a common point called the vertex of the angle. So here we have a comparison. This is a dihedral angle. This entire intersection of two half planes is your dihedral angle. But a polyhedral angle is now the intersection of one, this plane here, and the one at the bottom. They form a polyhedral angle. They meet at a common point, which we call the vertex. So in this case, this is the vertex of the polyhedral angle. So the intersecting planes are what we call the faces of the polyhedral angle, and the lines here are what we call the edges, the singular edge of the polyhedral angle. And then the face angle is the angle at the vertex formed by any two adjacent edges. So, for example, this angle down below, that's a face angle. This angle here is also, let's remove that. we're going to have this blue from here to here. That's also a face angle. The one down below here, mark it in blue, that's also a face angle. Even the one here, it's kind of difficult to mark, that's a face angle. And remember that the sum of any two face angles of a trihedral angle, trihedral would mean it's three edges, three faces or three planes is greater than the sum of the third face angle. And the sum of the face angle of any convex polyhedral angle is less than 360 degrees. So those are some of the common terms that we might hear every now and then as we go through the most important concepts in solid geometry, which is the mensuration of the most common solids.